Good afternoon. My name is Guthrie, and this is my partner, Michael. And this is our Flexure and Strain lab presentation. So we have a third partner, Mitchell, but unfortunately, he was not able to present with us today. He did really work on this presentation and all these other things. But yeah, so we'll continue on with this presentation. So our main objective is to use the strain gauges in class and to utilize the three-point bend test, which is what we learned about in lecture in beam theory to determine the Young's modulus of polycarbonate, which is a very common plastic in the engineering side of things. Our hypothesis is that strain gauges will provide a more accurate reading of the Young's modulus as compared to previous testing in our earlier labs in the year, and the Young's modulus of polycarbonate will be much lower than the metals tested in previous labs. So in our methodology, we had a main setup that we've used with the Mark 10 test stand. This has been used to measure the stress in previous labs and the strain, as well as many other types of stresses. We mainly use this to provide a stress in the center of the polycarbonate to measure the strain on its top, or the tension and the stretch of its top and bottom ends. And we designed and we put a reader on the polycarbonate, which is what the strain gauge is. And how we did that, for example, in figure one, we have a kit where we scratch the bottom end of the polycarbonate, and this is essentially a method to place the strain gauge in the most accurate of spots, aka the center where most of the load is placed. And then in figure three and four, these are the testing readers. So that's the Mark 10 test stand. And in figure four, we are measuring the difference in voltage to calculate the observed strain. And then we're going to compare it in our next slides. So our procedure, I said it a little bit in the previous, but we're going to prep that sample and we're going to put the strain gauge on the polycarbonate. And then our experiment one procedure is we are going to do the three-point bend test to calculate that voltage. And then we're going to repeat that process in experiment two and then calculate the percent error.
This is like, as you can see in figure five, it's the load displacement curve of polycarbonate. And the load was calculated by multiplying the pounds per force by the unit measurement to get it to newtons. And the displacement was taken from the displacement reader on the Mark 10 test stand. And from this, we were able to get the graph of the load displacement. And we were also able to find the slope of the load displacement graph, which, as you can see, is 4,026.7. And then in figure six, we have the stress versus strain curve of polycarbonate. And the strain was calculated using the equation below by taking the change in length divided by the original length. And then the stress, which is in the y-axis, was calculated by using the equation mzy divided by izz. And from this, we were able to, again, find the slope of the graph, which was 6,864.9. From those previous um, graphs, we were able to calculate the values of the strain of polycarbonate. And in experiment two, which is what those graphs were used for, we can use the slope of those graphs, which is seen right here in the equation E under next to experiment two. And we were able to multiply the slope by L cubed divided by 48 times IZZ. And from this, we were able to calculate the Young's modulus of the polycarbonate sample. And in table two, you can see in part one, it's the Young's modulus taken from the load displacement curve. Part two is the Young's modulus taken from the stress strain curve. And then three is the literature value. And from the literature value, we were able to calculate the percent errors. And experiment one, where we bended the polycarbonate sample along a radius, we're able to calculate the strain taken from the voltage input and output, and then we're able to calculate the theoretical strain from the equation. Strain is equal to Y divided by R. And from this, we were able to calculate the percent error as seen in table 1. Um, in this figure, we have the 3-point bending of the polycarbonate. This is supposed to depict the bending shape of the polycarbonate during the 3-point bend test. And from this, we get this shape by taking the displacement on the x-axis and the beam deflection on the y-axis. And to calculate the beam deflection, we have V of x is equal to the load times x divided by 48 IZZ times 4x squared minus 3L squared. And this is, as I said, is supposed to depict the shape of the 3-point bend test. It does look a little bit different from what we were able to observe. However, it does have that similar shape. And the reasoning behind the difference in shape is those percent errors as seen on the previous slide. Without those percent errors, the shape would be much more accurate. And the yellow dots can be, those are the first half, and those were calculated from using V of X, and then they were mirrored over using the orange dots to get the rest of that shape. And discussion, the polycarbonate we were able to find has a low Young's modulus. This means that it's much more, it's less rigid, and it requires a less force in order to cause deformation. And this is can be supported by the hypothesis, which we said earlier, that we'll have a low Young's modulus. And then our percent error, reasoning behind the percent error is mainly because when we first were setting up our experiment, the strain gauge was broken and the soldering came off. So we had to use a strain gauge that was already used in the previous lab. This means that the properties of the strain of the polycarbonate were changed a little bit due to the force being placed on it in the previous lab, as it already went through 3-point bend. And this would have changed the values taken from the voltage and the displacement, which would then affect our equations. Another reasoning that could cause percent error is that strain gauges simply aren't an accurate method of calculating the Young's modulus. It is the best one we have had so far. However, it could still not be as accurate as other methods out there. And railroad applications, using this test, we can determine the properties of the polycarbonate or other different materials that could be used during this test. And we could use the property materials that we found, such as the Young's modulus, and compare it to the certain needs of a certain application. So, for example, if you're building something that needs to stay rigid and hold something without bending, then polycarbonate might not be the best sample for that, as we found it does have a low Young's modulus, meaning it can't handle as much force as other materials.
So overall, in our conclusion, we concluded that polycarbonate has a low Young's modulus. This is seen by our calculated values of the strain of the polycarbonate and their percent errors. We can notice that when using the radii in class, the foam radii, that our theoretical and experimental strain, the percent error is, a little bit greater than 30 on our smallest percent error. But what's really interesting about that is that since it's a very small strain, in the grand scheme of things, it's pretty accurate compared to the theoretical strain, which is quite interesting. And then in our second experiment, our Young's modulus remains to be small. The percent error was slightly bigger, but it supported the fact that the polycarbonate does indeed have a low Young's modulus. So, and thus, our hypothesis was supported. And as Michael said, there are broader implications of this mechanism. So overall, we do not advise polycarbonate to be a more rigid material. And we concluded that our tests using the equations that we learned in the second sort of quarter of the year on the moment of inertia and the other equations, we can conclude that these are actually very accurate ways of calculating the strain. Um, and in the E equals the P over displacement times the L cubed over 48, we can actually multiply that by the stress to get a strain that's very close to our calculated value. So it actually kind of all loops in back on itself in terms of the equations and how you can use them. So I think the implications is that now we know a lot more about how we can manipulate our values and use these equations to our advantage when calculating things like stress and strain in the Young's modulus.
Recommendations. It would be recommended that next time when going through a process like 3-point bending, it'd be better to use an automated force application. This means something that is causing a force at a constant rate rather than us cranking the wheel. This would make it much more accurate as it would as the displacements would be much more steady as the forces steady. And another future work recommendation would be a 4-point bending test. This could also be used just like 3-point bending, but it would be another way to calculate the Young's modulus of the polycarbonate. And these are our references. Thank you.